In this video, we'll look at a second example of a KB calculation. That is, we'll have a concentration of a weak base and we'll calculate the pH. And also we'll go ahead and we'll do an interesting problem where if we're given the pH, we can calculate the KB. So these are kind of two for you. So here is pyridine on my table right here. And it's got a KB of 1.7 times 10 to the minus 9 molar. So what is the pH of a 0.1 molar solution of pyridine? And so go ahead and calculate that, and then pause the video, work it out, and then we'll go through it together. All right, so if you've unpaused the video, here's how we're going to do it. So we're going to initially start off by writing an ice chart. So let me go to another page and we'll work it out. So we begin by writing the KB reaction. So pyridine is C5H5N, and it reacts with water, and it's in equilibrium. The water gives a proton, so it's C5H5N H plus, and really if you're not in organic chemistry, it doesn't matter where you put the H, plus OH minus. And then we set up our ice chart. We are initially using a concentration that's 0.1 moles per liter. Water is a pure liquid. We're going to ignore it. And we're going to go ahead and we're going to assume the hydroxide concentration is 0 to begin with. And of course, this would be 0. We fill out the ice chart. So minus X plus X plus X at equilibrium. 0.1 minus X, X, and X. And we were told KB was 1.7 times 10 to the minus 9. And this is equal to the concentration of products. So that's X times X over reactants. So 0.1 minus X. And again, if we let X be much smaller than 0.1, so if X is much smaller than 0.1, that would mean that is approximately equal to X squared over 0.1. And again, we can solve for X and check with the 5% rule. So how do we find X? So X squared is 0.1 times by KB. We want to find X, we just square root both sides. So X is equal to the square root of 1.7 times 10 to the minus 10. And we can solve for that. My calculator says 1.3 times 10 to the minus 5. What do we want to find? We wanted to find the pH. So we can't find the pH directly, but we can find the pOH. The pOH is the negative log of the hydroxide concentration. And the hydroxide concentration is just X. So we can take the negative log of that, and we get 4.88. And remember, the pH and the pOH add up to 14. So the pH is 14 minus the pOH. And so we can see that that is 9.12. And that makes sense. It's above 7 for an aqueous solution, and that's what we'd expect for a base. Now, we were a little bit naughty here. We didn't calculate the percent ionization, so we have to check the 5% rule. So is the 5% rule okay? Well, we just calculate the amount that dissociated compared to what you started with. And as long as it's less than 5%, you are golden. And so if you take X and you divide it by 0.1, you get a very small number, so 0.013%. So much less than 5% is dissociated. So it's perfectly fine to use this rule. So our error in pH is going to be much smaller than 0.01, which is really the limit of what we can measure. We'll just do one more short problem. So if we've got a 0.2 molar solution of a weak base, and it has a pH of, say, 8.99. The question is, what is the value for that base equilibrium constant KB? So pause the video, write out an ice chart, and see if you can get the answer, and then we'll go through it together. All right, did you unpause it? All right, so let's write the reaction. So the base reacts with water, and it is protonated, so it forms BH+. Plus OH minus. And our ice chart, we write ICE for initial change equilibrium. Initially, our concentration of base is 0.2 molar. Water is a pure liquid, so we ignore. We don't have any of this, and we're going to say that 10 to the minus 7 is going to be so small we could ignore. The reaction proceeds minus X plus X plus X. So at equilibrium, it is 0.2 minus X, X, and approximately X. And what do we want? We want KB, so that's the concentration of products over reactants. So X times X is X squared divided by 0.2 minus X. All we need is X. Now, we have the pH, so that is actually sort of half of what we need here. So remember, the pH is the negative log of the H plus concentration. So the H plus concentration, right, is 10 to the minus pH. And if we had the H plus concentration in here, right, this would be perfect. But we don't. So we can also look at the pOH. So remember, the pOH is the negative log of the OH concentration. So therefore, the OH concentration is 10 to the minus pOH. So how do we find the pOH? Well, remember, the pH and the pOH add to 14. So in this problem here, we're given the pH is 8.99, so which is almost 9, right? So the pOH must be 5.01. So the concentration of OH minus is 10 to the minus 5.01. And if we calculate this, we get 9.77, so that's a guard digit there, times 10 to the minus 6 moles per liter. And now we're home and dry, so we can just plug it into the Kb expression. So we just take x squared and divide it by 0.2 minus x, so 9.77 times 10 to the minus 6 squared over 0.2 minus 9.77 times 10 to the minus 6. Now you might say, well, can we just ignore that x on the bottom? And we might be able to, but it really doesn't take any extra time on a calculator. So if we plug that in, we get Kb. And with rounding, I get that to be 4.8 times 10 to the minus 10. So it's a pretty weak base, which makes sense because the pH was only a couple of units above neutral, assuming we're at room temperature. All right, that's enough for one day.